Okay. It's working. Wait, one more minute. Excuse me. Still kind of a little bit. Okay. Excuse me. I'll present on some of my work. The abstract is what we're missing. We decided to take a step back and really make this just stay with the because why not? I think simpler. And I just want to go on too much about too many different things. Right? So this talk, it's all about coupled oscillators. And let's start with some concrete examples of coupled oscillators. This is a species of firefly, completely forgot to check, it's somewhere in South America. And it's synchronized based on light. So unlike fireflies, many fireflies in North America, these fireflies they have their own intrinsic frequency. And then in the presence of other fireflies, they adjust their frequency just a little bit so that they start taking the fire all together at the same time. And this is an example of coupled oscillators. Right? The coupling is about the visual processing and the nervous system. And the oscillators are the intrinsic frequency at which they flash their lights, but this is a coupled oscillator system. People have studied this in the past, but as it's just exactly lining up with that in that part of the framework. I'm particularly interested in the case of coupled oscillators in what are called central pattern generators. There is a schematic of the nervous system of the crab, something very analysis, transitory analysis. To figure out the crabs and the class, which is responsible for the estimate notes. So how do they to generate their own rhythms in the optics of any other inputs? So the oscillations do when you happen within this cluster of neurons, the same way that the heart is a piece with the same way that the rhythms are controlled by the complex complex in the brainstem. And to some extent, we know what's going on with the neuron in the synaptic ganglion. This example, red is excitatory, blue is inhibitory, if I remember correctly. And it's the schematic is deceptively simple. And there's a lot of things we can understand, especially questions like robustness, because if you control the system in one way or another, it's alpha the nervous system or one of these clusters of neurons, and will just survive. Right? And then you can still survive and function just fine. And we have the ability to simulate a lot of these neurons in good detail, but at some point we just reproducing the system and not really know much from it. Right? We can simulate undertones, but you put that in a computer at this point, we really need to And so my focus, my ongoing research is about typify reducing these possibly very complicated learning equations into something that's attractive. So that humans can understand, but we don't have the same computational power. And the potentials to continue with the genes let's say that contain bursting neurons, these neurons with potential to just spike spike and then stay quiet for a while, and then it'll spike again, and then stay quiet for a while. So it's an example of bursting. Okay, this terminology like memory potential, oscillations, neurons, well, okay, so that somehow they just make without any extra inputs. So pretty fundamental to survival, and there's a general class of neurons that can fit rhythmically, that's like breathing and swimming and walking. And all of that, but neurons are ultimately heterogeneous. So, physically, mathematicians, when we like to simplify things, we assume that everything's homogeneous, everything is the same, and we can do some nice things from that. But in reality, biology is incredibly messy. And there was just questions about what heterogeneity is. Is everything working despite heterogeneity, or is it helping somehow? And also, the problem is really strong. And the combination of these three things means that clean methods are just not, clean methods for reducing oscillators are just not relevant for the most part. And
that's the heterogeneous, is that like the physiology of the cell or the signaling of the cell?
Oh, yeah, all of it. So, why would you expect heterogeneity? So, probably associated with basically implied like the enabling the practical body. All of these things are produced randomly. Yeah. So exactly. So it's not that we observe homogeneity, it's that homogeneity is nice. It's that's not immediate mathematical. So yeah. And so even if we were looking at breaking neurons, if we're just looking at regular oscillating neurons, the combination of these two properties means that clean method will just be relevant. Because to get a strong coupling, you can assume homogeneity, but everything's the same. Or if you add it you can assume weak coupling or some other limitation. And so there's a huge gap in the literature, and that's why we understand weak biological systems. Yeah. I mean, so if we think of an amplitude of the active potential. So this is a huge force or whatever. The weakness is relative. So we have a given amplitude of oscillations, and a weak means that the influence one oscillator has on another, if they're coupled together, that influence is only a few orders of magnitude smaller than the amplitude of oscillations. Okay. So it's going on some signal to some synaptic neuron. The response to that receiving neuron, the negative potential will changes by the millivolts as opposed to the workings. You can define, so this might not satisfy me because I'm still trying to. So it turns out that you can write down the so that the influences oscillators have each other as well weak. I guess what we're doing. Okay. So strong just means not weak in that case. And I'll show you what weak company looks like. So I just want to see different things happen with oscillators. So these are more artificial. So it's how to do any of these things. These things of Zagatinsky reactions, you can see the scale are big and small. Small because diffusion doesn't come out in this case. And if you want to model this, you have to see the spatial part. There's a small well that connects, a small channel that connects these wells. And the flasher that you see on this light, there's only the constant amount of light shining through, but the concentration changes or shows it out, and they will light through for a moment. And so the black and the white are you can think of them as like spikes in the neuron. But they do indicate oscillations are happening in each well. Okay. And the natural question is based on the developmental topology of these things, what are the possible patterns that can exist? If you get here, what I want to say is an actual pattern that are exactly different from the performance variable. When you model it, it's something like 4 variables, but they could be a little bit more than that in the actual system. And here we can see that the center of the things to the outer well, involves the outer all these other synchronized, but we have different patterns that I'm not sure we do with different types of phase differences. Okay. There's how appearing different from the center compared to anything else. And then the outside, the phase difference between the outside as we see there. Okay. So underlying everything that we're talking about is the connection between phase differences and the underlying oscillations. Okay. So we said each component is always oscillating, each oscillator is going all the way all the time, but there are a lot of these differences between them. And this is an example of strongly coupled and homogeneous oscillators. This is an example of a pathological signal. This is induced by a empirical mechanism where the transmitter, and this was done in bats, and they cut a small window to be able to observe the activity, and they induce what's basically a mouse model of epilepsy. Okay. And this is an example that if you have symptom, it's really bad, and that is a pipe or something. Of course, not everyone's perfectly symptom, but technically bad because it's this epilepsy we want that. And part of my work, hopefully at some point, is to understand how we can better control these epileptic, these spinal things, and therefore control epileptic seizures. And there's been lots of modeling work and lots of clinical work on this. And there's you can do brain stimulation or do some kind of stimulation with a single current in the brain, and the modeling stuff. At the scale of the brain scale, you can say a lot of things, but I care about those details. I can't tell all things, and this is only an impossible application of my work. But we'll see. Yeah, this is part of the it's both. So yeah, they recorded from actual patients that were having small seizures with spinal waves. So I guess that would be your things on. We're not going into too much detail. And then they have the patients have testimonies that will help people those seizures. It's invasive treatments and just the tools you can take to help mitigate that. But in brain sedation, and we also have instances if it's something like power and processing. But so very, very invasive. Deep brain stimulation, there are questions about the correct frequency. So the questions of control are not out of it yet. Okay. So that's a bit, and then that's what I'm all companies probably talking about do this outdoors. And finally, so again, with the really good to see the version, so I still don't know how to do this talk. But at least in terms of the concepts, this is what we'll be looking at. Okay. So on the we have the time cases, time cases of two oscillators, and I'm plotting of course just one variable. We can pretend like this corresponding with flashes of lights, and the reaction we can pretend like these are the memory potential with two different neurons, red and black. Then we have the two oscillators, applying one variable, and in the full simulation, we have observed these some initial condition where the sort of this complete value that test together. With what they're called, they can be neurons that are synaptically coupled. They could be DC reactors that are loosely coupled with a full well. But we observe effectively this down in this cartoon is that they go for a sleeping. And so the phase difference first is zero. So that's symmetrical. It can be symmetrical, but they both can just some sort of community or ability to get one into the other. Right, right. Yeah, so this is absolutely kind of the company. You generally get this between different local contributions. So in general, this would be symmetric. And in particular, yeah, also for the Jewish operators. Because the sequence is always going to be a fixed point with level 7 oscillators. So there will depend on the coupling, but always, yeah. So we pretend we observe this. And what we probably think it gives us, and I'll go through this just slightly more detail in a moment, but what it gives us is this plot. It's a one-dimensional equation. Phi and call it a phase difference. The phi dot would just be this plot, and what we're saying is we started to make a condition close to synchronous. How about speed to the period? It's everything's mod t, so t is 0, 0 phase difference. And we don't really stability with one-dimensional ODEs. If we start here, we have the solution that was phi the variable was capital T or simply, and that coincides exactly with the third model behavior. So when you could have the entire function so involved in less is one. Exactly. So you can add something that adjusts the frequency of the oscillators, and that will just deal with the restrictions back up. Yeah, exactly. You can drift and you can put it back with. Yeah, exactly. So yes, yes. And just to really drive it, if we initialize the full model at some initial conditions with the frequencies close to examples. But when the time comes between those two for like it's roughly half a period. Hypothetically, we observe that we start to converge towards this quarter period with big phase difference. In the weak coupling theory, we'd be able to observe the stack as well. So we initialize this piece of it, and it's just a one-dimensional at this value, and then the weak coupling theory would coincide exactly with the full model. Okay. So you're only concerned with phase difference, not yet. Yeah. So it turns out to think about phase differences. If you even talk about phase differences, there are cases where you do not worry about amplitude, but you can still reduce this to just phase. That's actually the entire talk. Yeah. And what I like to do is abstract a little bit. So the full model simulation, instead of looking at time cases over time, I look at phase differences over time. And what this is showing is that different initial conditions. Some here this initial condition from phase difference happens to be unstable, but I initialize the operator the phase difference roughly here, so that phase differences will converge to the cycling. Here will converge to whatever the phase differences and so on. Okay, so this plot will see by the board. Any questions about this?
Are you coupled to us?
Yes, yes.
Okay, so this will project over two-dimensional.
Yes.
Each one will have to adjust its phase to the other one, right? Or how do you?
Each one has a phase, so you can reduce each one to, as in the absence of you reduce each one into single phase world. That's always true. You can just use time for that. But it's a pure actually it doesn't solve for stack because it's dynamic system.
So question, you're just looking at the difference of two phases.
It's because no. So we do have to take an average on. So you have to assume something about the. So epsilon in the classic case doesn't have to be small, but it just so happens that with the phase difference, the right-hand sides, the phase difference shows on the right-hand sides. That is because you can transform, you can send children because of the average part, and you can get the phase difference to show up on the local. And so you have, I'll show it level. Yeah. Again, this is why I might not be so satisfied for some people. But yeah, I'll keep going. So, that's the example. This is an example of biologically at the level. And that's a thing the synaptic wave. And this is just percentage dynamics. So if you've seen like hot chemistry, I mean, this is a version of that. Very similar, at least in principle. And the detail here accepts that there's this parameter that controls the strength of the synaptic thread on the level potential dynamics. So this is what I can call epsilon. Yeah, C is to capacitance, and we typically take that to be 1. Yeah, so this is capacitance times current is equal to all of the currents that move up and way. So it's sodium, the weak current with sodium ions and potassium ions. This is called I forgot which might be some kind of calcium current or something. And they all have different dynamics based on when they're open as a potential and limited potential. So it's the conclusions that I'm not showing. And I'll show you the thing later, actually. I'll say the cloud as well. I'll show you that later. So for now, we'll take it for granted that we can see what this
I'm just looking at Mountain J now.
okay.
Yeah,
So
that's where it's connected.
yeah. So this is yep.
So the UET itself will be called.
Yes.
Change the way you change the and you have currents on the right.
Yep.
Also. So C should be dimensional. That's the plan.
Yeah, it's all 17. So, yeah, so let's see. Hold on. So this is, yeah, that's not because this is 1 over resistance, this is voltage, and then, yeah, what is W? W might be,
Also, you back to the left.
yeah, we're going to see.
Right? So you want to match the limit.
Right. So, yeah. This is the one chart that actually what I can see the units as far as trying to think about it. Yeah, what's the
So
this is the DVT literally equals to I, but then C is yeah, that is I thought that was, but oh, it's next charge. Okay.
well, that's in coefficient. Yeah.
It's in units of, it's also
So it basically gives you the potential difference in the function of charge, right? So that's that.
It's like that. So,
and all of that.
It's not easy. It's then this should be dimensions.
Yeah.
You know, sorry, Youngmin, go. Okay, we'll worry about it later.
Okay.
But it's always positive, so that's, or you want to decide to be on.
No, it's just one. Always have to say which we want. There's also units of space in there, not that makes a difference, but yeah, let's come back to it. I'm actually really curious. Yeah. Okay. We'll consider this. We have 2 of these guys. They're coupled somehow. Okay, this is synaptic coupling, but they have some influence on each other somehow. And in this parameter, that's in front of the coupling term is small, okay, 0.2. So 0.2 is 3 to 4 orders of magnitude smaller than the magnitude of oscillations in this model. Then we can get this right hand side for weak coupling theory. We can see there's one stable fixed point and then one unstable fixed point. And when we indicate conditions for in the form model, we track the phase differences over time, along the variance to coincide with the weak coupling theory events.
So, you're right, it is the point. Okay, because even is not correct.
Oh, okay. Okay.
And so, but if Q is C and B, that's true. We need to work that is. So DQBT is C and B, assuming that the capacity is going to pass.
Yeah.
Right. So,
And so it's okay. Okay. I mean, yeah, that's enough. I appreciate it. Okay. And so the simple question is, how far can we push this weak coupling theory? So I just increase this parameter, this coupling parameter is something bigger, which really not that insane. This is a completely biologically relevant reasonable. But the weak quantity is the same. That's just a single one-dimensional unit. I have silence still of a function of that input. But why that's still a little bit off. But anyways, it just it's the amplitude figure. And we still have this anti-phase, the same initial conditions. But we seem to get these other behaviors. Here, it's not synchrony. We can plot over time and then see this is not synchrony. So there's something else going on in the frame model that the original theory can't capture. Okay. Yeah, and these lines are really interesting because I'll answer them and ask questions about that. Yeah. One thing, that answers my question. Only one thing. Yeah, no, absolutely. It's certainly the way you have marked from the behavior, you don't have marked on this sort of thing. Yeah, so this is not the fact that theory assumes the theory that I'll show the essential of this was shown that we assume we start from the uncoupled oscillators in the uncoupled period. So the increase in coupling that underlying limit sample is going to just deform more and more. And we're going to get so the transients we can't really necessarily capture. We can with other simple methods from what I'll show. What I theorize that is really the long-term behavior. Yeah. So I think it's messy for the reasons that makes sense as the results. Okay, so the weak coupled theory in summary, because this will help hopefully understand what I do for the non-weak theories. We have a pair of vector fields, plus times a term. The problem that I put in the text because I can't decide if I should include the specific form, which is not that crazy. This is G of xi xj. It just has it just controls the inputs from the other operator. But nevertheless, if we have enough logs sufficiently small, we can make this direct transformation where we don't can actually compute this function very easily. Everything about this is known. And then once we have this equation for the two operators, we can write down the different dynamics and we get the right hand side. So I'm skipping a lot of steps. There's average involved. There's that whole transformation under the interval that gives you the difference on the right hand side. But this is the high level conceptual part of this. So the takeaways from what I've shown for the weakly coupled oscillator theory is that with these two coupled oscillators, no matter how complicated they are, how many dimensions they have, no matter how many reduce those changes variables. So that's one weak. And the fixed points in this reduced sequence one dimension we capture the long-term phase lock with all the phase differences. Now the topic will create the phase differences over long times. These are the plots that we've seen. It's all generalized it's n oscillators in a macro way. You can get n algebraic equations and n unknowns. You can start without traveling mixed points. No, so unstable just means that the phase difference, if you start close to that phase difference, you'll away from that phase difference. So it does capture the instability when things locked in phase differences. You ever give the increasing down the circle here, so one might order is yeah. So that when you get those problems. Absolutely. So exactly the place that you mentioned that we shift. If I'm so we shift that function just so that it's touching the x-axis, so we get exactly that. Yeah. Yeah, so it's how many systems, so better bifurcations you can get in many systems. Well, some of them, yeah. It's just so nice and intuitive, you know. And all right, so what I want are these same benefits for stronger coupling. As I mentioned that there are a lot of different methods to reduce phase dynamics, but by far, I think that the weak couple oscillator it's as general as we can get it to be. It's just that the coupling has to be weak. Okay, so that gives a serious limitation when it comes to biological applications. So That's a good reason why I want to go to epsilon non-weak. That's what I mean by strong. Okay. Oh no, just non-weak. So in weak Gottlieb theory, epsilon is necessarily small. But that's just to allow you to do like a first order theorem expansion, basically. But here, the big picture is that I'm taking epsilon non-weak, or I'm trying to find terms of attack expansion that can go beyond the first order, beyond first order accuracy. For epsilon. Okay, so here are the active graduate stuff that I'm telling you this. Right, here that goes on the case to any of this two operators, and the problem is this very general form. Okay. We have some assumptions about the smoothness, so everything this has to be sufficiently nice. We have a tree theoretic sort of looks like now, when epsilon is 0. Is everything we say this? I think that we're doing over track over time. If you have extra slide, it's going to use a quick pressure, but okay. One technique persists. So in the new thing, the cycle is so this is not convincing, but still it's useful a lot of things to say, but not necessarily small. So and then uses some general speech function. Right. What diagonal? Oh, it's one of the extreme of G0. Oh, not necessarily. Yeah, so you can have so you can have a term for self coupling if you want. You can have, yeah, so you can have I mean this can just be the next one. If there's other trust. No, the coupling one there and fictional synchrony from G0 not I would say not necessarily. Not necessarily. It's the G that will have an entire its own dynamics. In the case of neurons, even if they're synchronous, it's a set as they're turned around the surface, or they do this kind of they'll do light, they'll do this slowly, but they're always doing that, whether about the afterwards or something else. Yeah. Okay. So transform the system into the theta variable. To do that, we actually could just use straightforward chain calculations. This is also a bit similar to the weak coupling theory case, but it's just basically pursuit the definition. There's the chain from d theta 1 dt, and then dx 1 dt, this is going outside. Distribute the dot product. And then we're about phases and everything that allow us to reduce to the values of 1. And then this term is kind of the key part. So far what I've done, I've reduced my propagated filter into a where but what I want to do is move along with this natural frequency. But what I want to do that natural frequency is affected somehow by the coupling and this additional term. Okay. And that's on weak. We know exactly how to calculate that term as I mentioned earlier with phase response curve. That's what this is. We know how to compute this in the case when outside weak. Now with coupling, this gradient term depends on the phase psi, which is amplitude. So now that we're far away from the limit cycle, and obviously the limit cycle is very strong. The period would be, oh yeah, so the period would be, the way that we assume the capital would be the period of the oscillator. But okay, you can define the phase. So you can define the phase to 5. You can 0 to capital T. So it's totally dependent on the individual. But nevertheless, this is you get the natural frequency plus some derivation. Okay, so now that we're looking farther away from the limit cycle, we have to start to look at amplitude. And there are technical reasons why some cases we don't calculate on this. I'll take a different that we do this. And by a similar set of calculations and their own set of assumptions, we can reduce the amplitude, we get equations for this amplitude variable. So kappa is the flow exponent. So if you offer the very immediate value, this will have a, this will not be able to. And then of course, in the opposite calculator, is the change down to the limit cycle. And then, yeah. Which it's a relaxation, but it's cap is negative. And so in the opposite problem, this variable will just became to zero, actually. But yeah, in terms of friction, I'm not sure about that. Yeah, exactly. So yeah, so the solution is wants to come back a little bit cycle, but if you couple, then you might get like the downward and down might get pushed around a little bit on the way back. Okay, so this guy is creating qualifies amplitude shifts. There are ways to calculate this, but for those, even in the case when F1 is non-weak, these equations, okay, you know, together, these equations, it's possible to compute all these terms in these equations. That's perfect. Okay. So this is how the phase changes as a function of the coupling. And this is how the amplitude changes as a function of the response to the coupling. And they one of those little recently in the past 10 years or so that people doing to figure out how to calculate this efficiently. And so it's all really common because of some work by finite quality things and we really calculate that with people behind that to calculate those arbitrary. But point being, we know all the terms here, no matter who they're otherwise. But what we've done is reduce the system of two equations and variables into field equations. Okay, so it's a pretty good reduction. But I want to do more. I want to get one phase difference variable. So the rest of this is, I want to kind of skip this a little bit because it's an expansion in the amplitude function and then an expansion of the epsilon in the complement strength of the amplitude variable. So an expansion, we have to just explode like crazy. And that's the idea of some kind of average to exactly. That's all it is in what we call it epsilon. Like with things that work in the phase, in particular, this expansion for the amplitude for the conductance for satisfied some linear with the not sure the functions that we kind of solve and then the phase and then do some work and then that's different solve that we see in the numerical. That's going to overrate the amplitude equation. And that's through that. I just it's not that it's hard, it's just second lesson there, unless to talk about what this is. Okay, so once we eliminate right, so it's epsilon, whatever epsilon or whatever properties of the function that you take into expansion. All I'm doing is computing coefficients of the Taylor expansion. So it depends on, whatever the convergence is, it's going to depend on the properties of whatever function we're looking at. So yeah, these guys, yeah, so then exactly. So that's what I'm saying. If you plug this upon expansion into this, you get a linear ODE form, let's say K from I don't know 50 between still minus 1 and negative terms. And so if you can compute this, and then we can use expansion, that sounds wrong. But if you can compute that first term, that can show over the closing function in this ODE, and then we can compute this. When we have that show over the closing function in this ODE, and so on. So I don't know if that helps. It's because the lowest one is zero. Epsilon, so psi I, and epsilon is good, I'm just and maybe on zero. Yeah, so in epsilon, the velocity was just because of zero. Okay. So epsilon zero, one of the assumptions I really say is this means that a lot of time we're looking at we're ignoring transients. Okay, well, okay. So yeah, which solid in the so we're not finding zero here, it's consistent with that assumption. Okay. One way or another, we can eliminate this. I say I put that in quotes because you have to do that you can do. Because we get explicit equations for each of the PIs, and then we can put that into the third equation, and then we just have one phase variable oscillated. And again, just skipping a lot of things, but the next step was to take the average and bring that results in these equations. And we can see that in each of these terms, the functions of the phase difference. We do that by one of the variables on x plus theta, and this would be that's theta 1 comma x plus theta 2. And then using external this we can do a calculation to get the inputs that was just a phase difference. Okay. Yeah, I can show you if you'd like at some point. We can have the same thing for all these higher order terms. And yeah, so these are MIs, either the derivatives of the coupling function, which we get out of the expansion cell. And we can see that they're all functions of I should have put this a different variable, but we can make an explanation so that we end up with something now and the integral. Okay, just a caveat, I use first order gravity theory. And if you're familiar with this method, you can do that on small, that's one of the fundamental assumptions. But I just, my climate events, I just really with this. So let's just see what happens. And so this is a presentation, I'm sure that we saw that in practice, this actually wasn't really good with the results. Not in the way we had it. And that's because we have more methods that go on, including this. But for epsilon, about too large. That's why we have having methods to think about that. I'm not sure what that looks like. Maybe off-the-shelf methods for high-level averages that we can use if we have to. That would be exactly what it's framework. So finally, second order problem. The drill, because I think have to drill without anything averaging. I still haven't explored exactly how the averaging would help. So I don't have a good answer for it. Okay. But however I derive those equations, we can look at the phase difference and write everything as just one phase difference equation. Write it in powers of epsilon. We have the lowest the plastic Greek quality theory, which falls right out of this method. Second, we got to look at it by beyond, and I put this in there because someone said, "Oh, you're going to," I was giving a job talk, and they said, "Oh, you're doing this like you're going to high order." That seems hard. And I thought, well, it's a job talk. I'm not going to give an easy presentation. But anyways, yeah, it's not ending on. I mean, principally, it's how we do what. And the cool way is that we have, it's not really described the three different styles, but that's why not necessarily small. So because things like authenticity just doesn't really that. And it's just true, like, and that's practice. So that's what we can do maybe 5 years. But in general, you have really have different functions, and they wouldn't necessarily use it universal.
That's one point, whatever, so, 2 had its own paper, 3 had its own paper. I mean, is it something where you think you're able to generalize it? Or we beyond, like, you have this like, okay, 4 plus, it's 1, and you have 2.
Yeah, so we can go with that. And I think I understand the question.
Okay, so you have these different projects, then you're putting them into paper, and like, I can review a paper where it was like, they made one little incremental thing, and it seemed like they would do, okay, for every slight modification of the model, I'm gonna come out with a new paper, and I was like, would you just put this on the line? And so I'm kind of curious about, like, because it's been right for the 2 and the 3 to put 2 separate, paper.
This
Yeah, it sounds like, right, so it's the computation, the specific computation, that's why it's taking up so much time, but the theory of, yes, it exists, so yeah, it exists.
I'm severely understanding how the point of this paper was.
Yeah.
So this is roughly 50 years, 60 years old or so. So no one really has any sense of how to move beyond that for the leap up theory. This showed results that are tangential to what I'm showing, but this paper was a very good paper of its own right. They're able to show, they're able to do equations that people had hypothesized were true, and I'm willing to show the confirm calculations that we probably didn't even get to begin with. So this is a lot in this paper. And then what I did was I noticed that it seems like there's something here that can generalize, in particular the expansion of psi, where psi would be epsilon G1 plus epsilon squared G2. Well, what we looked at epsilon G1, like the first order expansion of psi. I said, why not look at higher orders? So this is just, this is the beyond part. So this is the whole, well, in terms of this has the 2 last papers. Okay, so here's the thalamic model again. And this will be the last example, and I'll just finish after this. But yeah, here's the synaptic variable that kind of looks like we call it like an algorithm function that lies between the case. And so that really puts onto the model to the voltage set is going to be affected by the synaptic resting potential. This resting potential. But anyways, that's like just some light from this model. 4 variables, really messy. We can do some numerics on this, but we can say something more. Same thing from earlier. Really quick coupling theory with this whole quick coupling. But here's the only form not in green from my work. And then the bottom is the kind that has the closest for the models. Tell me what that's. The high starter coupling, order 1's the same, but the 4th order we capture these new fixed points appeared because the connections to the weak couplings will allow things to show you the function of epsilon, and these fixed points actually correspond exactly to the yeah, right. Exactly. And it was it's important because this is a very biologically relevant value. Not everything in biology is arbitrarily small. So this result and somehow we provide that with functions to collect to provide the stability and the difference dynamics. We did have this caveat of first averaging that something worked out. We did generalize to n oscillators, and in fact, that's the work that will be accepted soon with revisions. But it turned out if you have n oscillators with a stronger group, that you end up with exercise sufficient complexes. And so this sort of might be complicated than what is fascinating. But yeah, we know that's what extended small often solutions And that's the first thing. And I will with that, thank you to my brother, who's at the time of the guy who found it. The highlights, and thank you for your attention. Questions?
Oh, so I think maybe I'm missing what you do. So we do have like all of like any of the orders. So when so with that model, so maybe that you this. So how did you like the worst things that depending on any model, if you increase that coupling, then it's supposed to be need to increase the order until you see
Yeah, pretty much. So the question, these questions about like, I think even the methods of these are pretty inefficient but not accurate. So there's a lot of numerical questions behind this, you know, because my focus is on optimization. So there's stuff like that, and like the question of how far do you need to go, that is something, how far do you need to expand the material expansion to get what you want. It's completely depends on the function of what you want, right? So it's just one of those things. And yeah, exactly. So I went to second order, and we see what I wanted, third order, and see what I wanted, fourth order, oh, something happened. You know? Cool. Okay. So I'll finish here. Yeah, thanks. Bye.